might even put it on stellar and just close with this. So suppose A is m by n, B is n by p, and C is p by q. Okay. How many steps does it take to find A times B times C, the product of those three matrices? Well, if I go this way, I have to multiply A. I have to do BC first. So BC costs, how many operations to multiply that times that? NPQ. Nice formula. NPQ. Why is that? Well, I could say that the answer is n by q. And every number in there was an inner product of a row and column of length p. So I have nq inner products, and each one costs p multiply adds. And then, so now I have BC, which will be now. So now I have m by n. Then I have m by n, which is the A, times B by C, which is now n by q. That's BC. This is A, BC. So in this one costs, what's the cost here? M by n, n by q. By the same rule, it'll be m, n, q. Good. That's the first way, A times BC. Now the second way is AB times C. And let me write in again m by n, n by p, p by q. So now I'm doing this first. So AB costs, tell me again now, what's the rule for the cost of a matrix multiplication? MNP, MNP. And then I'm multiplying m by p, that's AB, times p by q, that's C. So I have MPQ. So I have that together with that, or that together with that. That sum, those two or these two. And they're different. And let's just recognize the most important example. Suppose C is a column vector, C for column vector. So Q is 1. There's only one column. So if Q is 1, this way did NP, let's just specialize to that. So specialize to C equal a column vector, which means that Q is 1. I only have one column. So then A times BC is versus AB times C. So let's just figure that out when Q is 1. So NPQ is just NP, and MNQ is just MN, where AB is MNP. Oh, that's a bad one. Disaster already. Multiplying, those are potentially two big matrices, multiplying a column vector. So here I've done a matrix multiplication. I never should have done that. This is a matrix vector. It gives me a vector. And then this is a matrix vector. So I get nice numbers here, but I get a terrible number for AB. And then I multiply that by C. So that's MPQ. MPQ. So MP is factoring out. So if I write it as N times m plus p versus this one is m that's factoring out times m, no, yeah. What's up here? Yep, sorry. What am I doing? Yeah. Is it p that factors out from this one? Okay. P times m plus n, I guess. Sorry. Anyway, the difference is.
I think it's mp times p plus
Sorry.
n plus q.
Shall I go over it again or write? Let me do just this thinking again. If q is 1, if I go this way, was that my final total when q was 1? And that's this? That's, no. M factors out times n plus p. Whoops. Let's just get that right. This is, oh no, n factors out. Sorry, n factors out times n plus p. And this way was all these things.
Both the m and the p factor out.
Both the m and the p factor out. Okay. Thanks. Times n plus q. N plus q was 1. Okay. The whole point is we've got this horrible multiplication of 3 big numbers. And this only had 2 big numbers. So this is orders of magnitude faster than that. And of course, you would have done the calculation that way. You would have multiplied the column vector by a matrix to get another column vector, and you would have multiplied that by a matrix to get another column vector. Where here, you crazily multiplied 2 big matrices together and then got a column vector. So it was there's the bad move. Okay, thanks. So I've passed the time on this ABC. It's just to show that on a very familiar calculation, you have to do it in the right order. And back propagation is the right order for partial derivatives. Okay, thank you. And so bring laptops Friday, and look forward to Professor Rao. Give him a good welcome.